Hello everyone and welcome back to another video. Today in this video I am going to show and explain you a very basic neural network. Using that neural network I am going to teach a car how to drive on the track. Please check the link in description if you want to download the source code, or check my Substack for written explanations. These are the requirements to run this program. Before start the code, please install these libraries with their version. If you have already installed, then please start coding. And also I am going to walk through each code and function step by step so you can understand everything easily. And also these is a config file. You can download it by checking the link in description. This Python code is part of a project that aims to teach a neural network how to drive a car around a track. The code includes several imports, such as Pygame, OOS, Math, Sys, and Neat, which are necessary for implementing the functionality of the game. Next, the code defines the screen dimensions as constants, screen_width and screen_height, and creates a Pygame display window with these dimensions using pygame.display.set_mode. The code loads an image of the track using the pygame.image.load function. The image is located in a directory called assets and has the name track.png. This image likely represents the visual representation of the track on which the car will drive. At this point, the code has set up the basic environment for the game, including the display window and the track image. The remaining code is not included, but it is expected to involve the implementation of the neural network for controlling the car and the game logic for training the network and evaluating its performance on the track. This code establishes a car class, a derivative of the Pygame.sprite class, designed to depict a car within a game setting. Within the constructor, __init__, various car properties are defined. The original _image captures the car's visual, sourced from car.png in the assets folder. Image mirrors the value of original _image. Rect refers to the bounding rectangle of the car's graphic, with its center pinpointed at 490, 820. Vel_vector, a 2D vector, is initialized at 0.80, directing the car's x-axis movement. The angle starts at 0, denoting the car's rotation outset. Rotation_vel is set at 5, showcasing the car's rotational speed. Direction also kicks off at 0, signifying the car's primary route. Alive confirms the car's active state with a true value. Finally, radars begins as an unpopulated list, reserved for radar units crucial for discerning and navigating around obstacles. In sum, this code meticulously sets the foundational attributes for the car, from its visual representation and position to its velocity, trajectory, and active state, while also paving the way for obstacle recognition with an allocated radar list. This code snippet is from a class named car, a subclass of Pygame.sprite. It plays a role in a game or simulation designed to train a neural network to navigate a car around a track. The update method refreshes the car's state. Initially, the radar's list, which holds data on detected obstacles or objects from the car's sensors, is cleared. This ensures that only the most recent information is taken into account. The drive method, which enables the car to move or accelerate, follows. This method considers decisions made by the neural network based on the current environment and the car's position. The rotate method, controlling the car's direction, comes next and uses steering inputs from the neural network. A subsequent loop examines a set of predefined radar angles, -60, -30, 0, 30, 60. For each angle, the radar method simulates the car's sensors, detecting obstacles or objects within specified ranges. This information gets stored in the radar's list. Post-radar loop, the collision method determines if the car has made contact with obstacles or track walls. Should there be a collision, this method updates the car's status or potentially concludes the game. The final data method captures and processes pertinent details like the car's position, velocity, and sensor data. This information may serve to train the neural network or fulfill other simulation requirements. In essence, the update method oversees a host of vital functions, ranging from driving to data collection, ensuring the car's effective movement and navigation. The drive method of the car class, crafted with the Pygame library, is engineered to adjust the car's position on its course. Within this method, the instruction self.rect.center plus equals self.vel_vector*6 alters the center attribute of the rect instance. The rect likely acts as the encapsulating rectangle for the car graphic, with the center pinpointing its midpoint. By utilizing the plus equals operator, the center property is enhanced based on the magnitude and direction of self.vel_vector, scaled by a factor of 6. Evidently, self.vel_vector denotes the car's velocity vector. By multiplying this by 6, the code ensures the car advances 6 units following the velocity vector's guidance. In essence, this segment facilitates the continuous motion of the car graphic along the track, steered by the designated velocity vector. The collision method, a component of the car class, diligently monitors for any potential run-ins between the car and the track's confines. The procedure is initiated by designating a length value of 40, serving as a measure from the car's midpoint to its potential collision locale. Following this, it evaluates the exact positions of potential collision on both the car's left and right flanks. The derivation of these coordinates integrates the distance from the length variable and the car's orientation angle, adjusting the car's central x and y values accordingly. Post this computation, an assessment takes place to discern whether any of these determined points match a green-colored pixel hypothesized to delineate the track's perimeters. A match signifies a collision event, leading to the car's alive status being switched to false, marking it as non-operational. To cap off, the method employs the Pygame library to visually depict these collision locales. Cyan-colored circles, with an RGB notation of 0, 255, 255, 0, of a 4-pixel radius are drawn, offering a clear view of these points on the display. The rotate method within the car class in Python is intricately designed to pivot the car's visual representation depending on its ongoing course and rate of spin. To kick off, the method evaluates the car's direction attribute. A value of 1 prompts a decrease in the car's present angle by the rotation speed and an accompanying rotation of the car's velocity vector. On the flip side, a direction value of -1 results in an increment of the car's angle by its rotation speed, simultaneously turning the velocity vector the other way by the same rate. Following this directional adjustment, the code leverages the Pygame library to bring the visual change to life. The car's base image undergoes rotation and scaling using pygame.transform.rotasm, oriented by the updated angle and scaled down by 10%. The modified graphic is then reinstated to the car's image attribute. To round off the process, the code revises the car's sprite's boundary rectangle. By invoking the get_rect function on the adjusted image and aligning its center with the initial rectangle's midpoint, the car's sprite maintains its original placement post-rotation. In summation, this method imparts a dynamic visual spin to the car's sprite, mirroring its direction and spin rate, enriching the experience of navigating the car on a circuit. The car class, pivotal to a project aimed at teaching a neural network the art of vehicular navigation on a track, houses a method named radar. The essence of the radar method lies in its ability to mimic a radar mechanism for the car. Its primary task is to ascertain how far the car is from the closest obstruction, in a direction determined by radar_angle. At the outset, several variables are established. Length stands at 0, denoting the gap between the car and an impending obstruction. X and Y are markers for the car's central coordinates. The narrative of the code shifts to a while loop, which is driven by 2 central conditions. The X, Y, pixel hue should not coincide with the designated color, Pygame, color, 2, 105, 31, 255, and the length must not breach 200. As the loop persists, it methodically amplifies the length, recalibrating the X, Y coordinates, factoring in both the vehicle's orientation and radar_angle. Upon exiting this loop, the Pygame.draw.line function draws an illustrative line from the car's heart to the pinpointed X, Y spot, effectively charting the radar's scanning trajectory. Complementing this, a petite circle emerges at X, Y via the Pygame.draw.circle function, acting as a beacon for the identified hurdle. Subsequent steps involve determining dist, the linear space between the car's nucleus and the X, Y coordinate, capturing the car's proximity to the obstacle that the radar's eye caught. This detection, distilled as the radar_angle, DIST, duo, is added to the radar's list, which serves as a reservoir for all radar insights for subsequent processing or evaluation. To encapsulate, the radar function within the car class is adept at emulating a car's radar system, proficiently probing for blockages in designated directions and logging the car's closeness to the closest barrier. The data method, nestled within the car class, is geared towards harvesting information from the car's radar sensors and fashioning it into a format suitable for the neural network's consumption. Initially, an input list springs to life with a quintet of zeros, ready to house the readings derived from the radar sensors. Following this setup, the narrative dives into a loop, meticulously sifting through the self.radar's list, which is the probable repository of the car's radar sensors. The enumerate tool is recruited to serve dual purposes, fetching both the index and the value representative of each radar sensor. As the loop unwinds, the script pulls out the value from radar 1, which is arguably the radar's quantitative reading, and diligently places it into its rightful position within the input list. To ensure seamless compatibility with the neural network, the value is funneled through the int function, translating any float or string entities into whole numbers. Upon concluding these steps, the data method graciously offers the input list as its output. This transformed list stands ready to feed the neural network, enabling it to craft informed decisions, all anchored on the insights harvested from the radar sensors. This piece of code is defining a function called remove that takes an argument called index. The code is indented, which indicates that the function is part of a class called card that is derived from the Pygame.sprite class. Within the function, there are 3 calls to the pop method. The pop method is used to remove an item from a list at a specified index. In this case, it is used to remove an item from 3 different lists: cars, GE, and nets. Based on how this code is written, it seems that these 3 lists, cars, GE, and nets, are related to a neural network training process. It is likely that each index represents a specific instance of a car, and this remove function is used to remove that specific instance and its associated neural network from the corresponding lists. The eval_genomes function, housed within the car class, plays an instrumental role in a venture that endeavors to educate a neural network on the art of vehicular navigation around a circuit. As an introduction, this function makes a polite request for 2 parameters, genomes, which presumably represents the DNA of the cars, and config, perhaps a set of instructions or settings. Stepping into the function, 3 pillars are erected in the form of global variables: cars, a probable garage for our virtual vehicles; GE, a likely DNA database; and nets, the neural nexus powering the cars. The heart of the function throbs in the embrace of a loop, diligently whirling until the run flag is lowered. Within this realm, an attentive subloop stands guard, ever vigilant for the quit signal, ready to halt the program should the user hint at an exit. A vivid portrayal of the track is then lovingly painted onto the screen. Following this artistry, the function assesses the occupancy of the car's list. An empty garage prompts the loop to gracefully curtsy out, drawing the curtains on the function. Subsequently, a parade of cars from the cars list unfurls, with each car's genomic counterpart in the GE list receiving a slight nudge in fitness. Should any car falter and succumb, it is gently escorted out of the list. With a renewed sense of purpose, the function embarks on another sojourn through the cars list. Here, each car's neural muse from the nets list is invoked, steering the vehicle by deciphering the whispers of the neural network. The directional decree is simple: an output north of 0.7 from the first neuron steers the car right, direction 1, while its counterpart nudges it left, direction -1. An ambivalent neural response, with both outputs dawdling at 0.7 or below, brings the car to a standstill, direction 0. Post these deliberations, each car pirouettes on the screen, adjusting its stance through the update method, culminating in a grand ensemble as the entire spectacle is refreshed for the audience using Pygame.display.update. The described code segment revolves around the setup and initial execution of a neat, neuroevolution of augmenting topologies, neural network within the confines of a car class. To break it down step by step. Imports: before any magic happens, the necessary libraries and dependencies are summoned. These facilitate the later workings of the neat process. The run function, a function named run, is unveiled, curiously asking for a config_path, the whereabouts of the sacred neat configuration script that holds the blueprints for our neural network structure and behavior. Constructing configuration: with the help of the neat.config class, a configuration object is birthed. This object, an ensemble of settings that dictate the nuances of the genome, each individual neural network, reproduction, species set, and even stagnation, is vital. It's enriched further with the secrets from the config_path, allowing for a bespoke touch. Populating neat, the cauldron bubbles again, this time to conjure a population of neural networks with the neat population class, using the freshly crafted configuration object as its essence. Adding reporters: to keep tabs on this evolving population, 2 vigilant scribes are added. stdout reporter: this one is the town crier, making loud proclamations about the champions of the genetic pool, the finest genome, the diverse species, and the ongoing generations number, directly to the standard console output. The true decree empowers it to begin its duties. Statistics reporter. This meticulous chronicler keeps detailed records of the population's feats and fables. Whether it's for posterity or future scrutiny, it ensures no tale of the genetic dance goes unnoticed. Commencing evolution. With a clarion call in the form of pop-run, eval_genomes, 50, the evolutionary carnival begins. For 50 generations, each neural net, or genome, will be tested in the fiery crucible of the eval_genomes function. Here, each one will strut its stuff, earn its marks, and the dance of natural selection will decide who stays, who goes, and who gets to be the forebear of the next generation. To sum it up, this segment ensures the car's neural network is not only born but also evolves, learns, and perfects its art through the generations, all under the watchful eyes of the neat algorithm. This Python script is the primary driver of your project. The check for __name _main__ determines if the script is being executed standalone or being imported as a module. Using this check is a common practice to ensure specific sections of the script run only when the script is invoked directly, and not when imported elsewhere. The script determines its own directory and assigns it to the variable local_dir using the os.path.dirname__file__ method. This is useful to derive paths relative to the script's location. Subsequently, it constructs the path to a configuration file named config.txt and assigns it to the config_path variable. This is achieved by combining local_dir with the configuration file's name using the os.path.join method. In the end, the script calls the run function, passing the config_path as its parameter. It's inferred that the run function is responsible for initializing and executing the neural network model that trains the car for its track navigation task. The provided config_path probably contains essential configuration details needed for the training.